So folks, the next thing we want to take a look at is the idea of an orthogonal projection of one vector onto another. And so let's try to build a little bit of intuition for that. So just let's go ahead and plot these two vectors here. We've got in R2. So we've got vector u and vector v. So let me give myself some coordinates here. It's a 1, 2, 3, 1, 2. That should be big enough, I hope. And let's plot the vector. I'm going to plot vector v first. So vector v is this vector right here. So there's the endpoint there at 3, 1. So there's vector v, if we're representing it as a position vector. And then vector u is the vector with that reaches out to the coordinates 2, 2. And so there is vector u there. Okay. So what we want to, well, let's, I guess just for practice, I have you compute this dot product, so let's do that. V dot u, and we're going to need it in the next problem. So v dot u is 3, 1, dotted with 2, 2, and so we end up with 6, we end up with 8. Actually, the same answer as our last dot product problem. Okay. So the next thing I want to talk about is something called the orthogonal projection of u onto v. So before we do that, I want to ask you about this object right here, which will end up being our orthogonal projection. But let's look at this object right here. What type of object is this? And I think that's a really good question, and that's something worth spending some time to think about. And that's something I encourage you to do throughout the rest of our vector algebra, and then when we get into vector calculus. You should always be asking yourself, what type of object am I working with here? And what we see is notice we've got the dot product of u and v. Well, what does that result in? That results in a scalar. And in the denominator here, we've got the dot product of v and v. Well, if we do that dot product, it results in a scalar. And so it turns out that this entire expression right here, the part in parentheses, is simply a scalar divided by another scalar. And so it is itself a scalar. And we're multiplying that scalar to a vector v. Well, we know that when we take a vector and we multiply it by a scalar, the result is another vector. So the answer to this is a vector. So let's go ahead and find this vector real quick. So we've got u dot v. Well, we computed that above. That was 8. And v dot v, well, let's see here. That's two ways to think about that. Remember that v dotted with v, one way to think about it is that's simply the magnitude of v squared. But you can compute it by a couple different means, I guess, or a couple of different viewpoints. But what we end up with is just simply 3 squared plus 1 squared, or 10. So that gives us 8/10 for that expression, and that's a scalar being multiplied to the vector v, which is 3, 1. If we reduce that down, we could call that 4/5, say, and then times the vector 3, 1. And that would give us 12. And here I'm going to go ahead and write everything in it's just a single vector with no scalar out front. So this would give us 12/5, 4/5 is this new vector here. I'd like to plot this vector on the graph. And let's see what would happen. Well, let's see, 12/5, that's a little bit more than 2. That's maybe right about there is 12/5. If we go up 4/5, maybe that's right about there. If I were to plot this new red vector, look where it lies. It lies right here, thereabouts. Okay? There's this new vector v, and I'm going to go ahead and label it, I'm going to label it P for projection here. And I want to talk about what we just did. Okay? And my drawing's not quite right. Let me go out just a hair further to just match with what I'm about to say. And you'll see how to adjust this in just a minute. But here's that vector P that I just came up with by computing this expression here. It ended up being a vector. And this is what we call the orthogonal projection of u onto the vector v. And the way I want you to think about this is if I were to draw a 90-degree angle, remember orthogonal can also be thought of as perpendicular sometimes. So if I were to draw a 90-degree angle that hits v at a 90 degrees, but also runs through the end point of vector u, you would see that where the 90-degree angle that ray ends up as is at the tip of our vector p that we just calculated. One way I think it's a very helpful way to think about it, our book talks about this, is you could think of there being sort of a light source up here. And if I thought about a light source heading perpendicularly down onto, so it's like maybe high noon, heat of the day or something, that light source is heading straight down onto our green vector here, you'll see that the blue vector u is going to cast a shadow. And where would that shadow be along our green vector? And where our p vector lies, that's where the shadow of u would end up on. And so we call p the orthogonal projection of u onto v. So that's where we're using that expression here. So this is the orthogonal. And I'm actually pretty lousy speller, orthogonal, I think. The orthogonal projection of vector u onto vector v. Okay? So we're going to use this notation right here to denote that. That takes a little bit of practice to read. So you would read this expression just as I've written here, the orthogonal projection of vector u onto vector v. So vector u onto vector v. That's how you read this expression here. My suspicion is that probably each book uses its own notation for how they want to write that. That's how our book uses the notation. So this is the calculation we just did to come up with that orthogonal projection, but I don't think it's entirely clear where all those components come from. So let's go ahead and rewrite this using the definition of the dot product and a little bit more about what we know. So the dot product of u and v we saw in our pre-work and elsewhere we've seen is that the one way to compute that, I guess, is to take the magnitude of vector u times the magnitude of vector v times the cosine of the angle between those two vectors. And then, as I said already, when we take vector v and dot it with itself, that gives us the magnitude of v quantity squared, and then we've got that all times this vector v over here. Okay, so I've replaced this expression in parentheses, the scalar component here, this way. Great. So what I'm going to do is I'm going to do a little bit more manipulation with this. I could rewrite this as the magnitude of u times the magnitude of v times the cosine of theta all over 1 magnitude of v, and then multiply that, careful, that's scalar multiplication there, I ought to be careful with how I denote that, multiply that to that vector v, but I'm going to rewrite this vector v as v over the magnitude of v. So careful here, this expression here is now a unit vector. Okay? And so what do we see? Well, in this scalar component, we see that we've got a magnitude of vector v divided by a magnitude of vector v. So I can go ahead and cancel those out. And if I do so, then we end up with the magnitude of vector u times the cosine of theta times this unit vector, vector v, divided by the magnitude of vector v. And this is maybe a more intuitive way of arriving at the orthogonal projection. I think this way is easier for calculation, especially if you're just given the component vectors. This way of writing out the projection is easier, but this is maybe more intuitive. By what we mean as far as the orthogonal projection of u onto the vector v here. So when we think of taking and projecting vector u onto the blue vector onto the green vector, that's going to happen by giving us, if you think of it in terms of that shadow idea, that's going to give us the vector p there, where we would have the shadow for vector u. Okay, so how can we look at that? I'm claiming this is more intuitive. Why is that? Well, a vector, to describe a vector, you need two components. You need a magnitude and a direction. Notice that this could be thought of as a magnitude, and then right here we have a direction. So because I'm dividing vector v by its length, so let me be careful here. What I'm really doing is multiplying it by 1 over its magnitude. That makes this a unit vector, and you can always think of a unit vector as something that just assigns direction. When you interact that unit vector with something else, all the unit vector contributes is a direction, and it doesn't modify the length of the vector in any way. So this gives me the direction, and this gives me the length. And so what we can think about this is this computes the length of vector u when we project it onto vector v, and that ensures that we're going in the vector v direction there. So we've got both length, magnitude, and direction here in this formulation of it. Okay, so be careful here with the notation, folks. And this is again where I think probably different books will do this differently, but we read this as the projection of vector u onto vector v. And that's going to be a vector that's in the same direction as v, and so another way of saying that is it's going to be parallel to vector v, as opposed to this expression right here. Notice that these two expressions are not the same. Look at the order here. This is the projection of u onto v. This is the projection of v onto u. So it's as if we did this thing in the reverse direction, and I thought of u as a vector that I'm going to shine a light perpendicular to that vector and see where the shadow of the green vector would lie. Oops, sorry to be jumping around on you. Okay, so let's keep working through this. We go ahead and write this as just the scalar component of the above projection, and you see that when I put it into this more intuitive format, there's the scalar component. And another way to look at that is that's the same thing as, well, this dot product here would be magnitude of u times the magnitude of v. Let me be careful with those time signs. The magnitude of u times the magnitude of v times the cosine of theta, all over the magnitude of v, and then if we cancel those out, then we would end up with simply the magnitude of u times the cosine of theta, which is what we said is the scalar component of the orthogonal projection when we think of it, the direction as just being a unit vector as opposed to the way we wrote it up here as whatever the original vector v was. Okay. So these are two different ways. I think this is more useful for computation if you haven't already computed the angle. This is a way of computing the scalar component of the orthogonal projection, and this is a way, if you've already got the angle, of computing that scalar component. Folks, here I make a quick comment that says I'm not going to refer to this that often. I find it a little bit confusing that this scalar component only refers to the vector when you have it in unit vector form. And so that seems a little bit confusing to me, because over here when we wrote the expression this way, we still have a scalar, which you could think of as a length modifier, times a vector, so times a vector, and so that gives a vector with a particular magnitude heading in a particular direction. But this expression right here does not give us what the book is calling that scalar component, and so I'm not really, because I find that a little bit confusing, I'm not going to focus on this, although you'll have a couple of homework questions about it. Okay, so let's just look at this one more time to see how all of this goes together. So if in this problem we're asked to compute the projection of vector u onto v, so we said before there's a few different ways you could think of computing this. I could go through and, so don't write, well, if you want to write this down, I could go through and write this as the magnitude of u times the cosine of theta divided by the magnitude of v times the vector v over the magnitude of vector v. I guess I need to put those lines over. Okay. You could compute it this way, but I don't think this way is very useful. Oops, do I have an extra factor in there? Let's see here. Yeah, I do have an extra factor in there. Sorry about that, folks. So we could write this as the magnitude of u times the cosine of the angle between them times vector v, or scalar multiplied to vector v, divided by the magnitude of vector v. But I don't find this very useful for computational use unless you already have that angle. So instead what we're going to do is we're going to use the first definition I gave you, which is u dot v over v dot v times our vector v. Okay, so let's go ahead and compute that. And I'm just going to do each of these in their place. Looks like we're missing the angles on there. So if we did u dot v, the dot product is, let's see here, 12 plus 4, that comes out to be 16. And if we took v dot v, remember that would be 9 plus 16, which is 25. And so we end up with 16/25 times our original vector v, which is 3, 4. And you could leave it like that, or you could go ahead and write it as 48 over 25, 64 over 25, either way. And you can see what we've done here is for our vector v, we drew a line perpendicular to it so that it went through the tip of vector u. And again, we think of there being sort of like a light source here shining down, and we are asking the question, what vector along vector v is its shadow? And we just computed it to be this vector here, or if you like, in this format. Okay. So then if we want just the scalar component, one way to do that is to just use what I gave you up here. So that would be vector u dot vector v all over the magnitude of vector v. And the dot product of the two is still 16. Careful down here, I'm just computing the magnitude of vector v. So that's the square root of the sum of the components squared. I'll go ahead and write that out. That's 3 squared plus 4 squared, or 16 over the square root of 25, which in this case is 16/5. And that's the scalar component if I were to rewrite this expression right here as a unit vector. Notice that this was not a unit vector, and so that's why that's not the scalar component that we call the scalar component of the unit vector when we project u onto v. So again, I'm not going to do much with this, but I want to show you how to do those computations so that we can be in alignment with the text. All right. This is getting a little bit long. The last thing I want to do is let's actually look at an application of this. So we've got something of an application. We've got two vectors, u and v. I've given them in column vector notation. And we want to express the vector u as the sum of two vectors where one of them is parallel to v and one of them is orthogonal to v. So I'm going to draw a picture here of this just so we can see where we want to go. Here I've got vector u, which is the vector 3, 4, so 1, 2, 3, 1, 2, 3, 4. So maybe we represent that vector u this way. So there's vector u. And then we have vector v, which is the vector 1, 1. And so maybe there's our vector v there. Okay. So what we'd like to do is we want to represent vector u as the sum of two vectors, one of which is parallel to vector v and one of which is orthogonal to vector v. So let's just extend v out, the line that is vector v, or that passes through vector v, and we can see what we want then. This is going to be our vector parallel. I'm going to draw it in black here. This is going to be our parallel vector that we want. And oops, I kind of went a little too far. Let me try that again. This is going to be our parallel vector, p, and then we want some other vector, n, which is orthogonal to the original vector v, that original red vector. Notice that this orange vector here is, that's orthogonal to the red vector. And so we're going to represent u as the sum of vector p and vector n, and we can see that as we line it up in our tip-to-tail method for doing vector addition. Okay. So it turns out that vector, we'll compute n in just a second. In fact, let me label this though. And I forgot a bar over p. So we'll compute vector n in just a minute here, but vector p, we can think of it. Notice that that is exactly the drawing that we just did when we did the orthogonal projection. So the vector p is really just the vector u projected onto the vector v. So we're going to go ahead and compute that as we just saw. Again, I think it's best to use this computational form rather than computing the angle between these two vectors. So we'll use u dot v all over v dot v times the original vector v. So if we do that, let's see here. U dot v is 7, and v dot v is 2. 7 halves times our original vector v, 1, 1, and I went ahead and put it into the angular vector notation. And so we get that vector v is the vector 7 halves, comma, 7 halves. And notice we see that, right? I mean, my drawing that I did wasn't the best, I was trying to look ahead as to where we're going. My drawing is not the best, but sure enough, yeah, you see that if you go out 7 halves, that's 3.5 in the x direction, and then 3.5 in the y direction. You draw the corresponding vector. I'll do it in black here. Yep, that's our vector p there. Okay. So that should be a little bit reassuring. So we've come up with a vector p. That is just simply the orthogonal projection of vector u onto vector v. And now we need to come up with this normal vector here. Okay, well, we can look at our picture that we just drew and see what we need our normal vector to do. As we said, the normal vector plus the parallel vector has to equal vector u, and so we're actually going to, rather than try to compute the normal vector, vector n, by some other means, we're going to solve a vector equation for it, and so we subtract over our vector p there. Okay. So let's see here. That's simply vector u, which was the vector 4, 3. And from that, we're going to subtract the vector that we just found, that orthogonal projection, p. And if we compute that, we end up with, well, it's 1/2 comma minus 1/2. And let's see here. Did I do that right? Did I copy everything correctly? Let's see. 1, 2, 3, 4, 1, 2, 3. Hey folks, all my math is correct here, but I've just realized that I plotted this initial vector u incorrectly. So let me modify the drawing real quick. So folks, when I drew that, I had I graphed the vector 3, 4 instead of 4, 3. So here I've redone my drawing. So that's our vector u, and that's our vector v. If we put our vector parallel that we computed in, if we put in our vector parallel that we computed into here, that's about here. So there's our vector p that's parallel to vector v, and is the orthogonal projection of u onto v. And then we had our normal vector here, which you could think of as being this one here. And so now my drawing matches what we found as an answer. That's why I was concerned, because that wasn't lining up. So anyway, we've now found that vector n, which you can see, yep, sure enough, it's basically a vector that steps over about 1/2 and steps down by about 1/2. And if you do that, then we arrive at vector u. So we've rewritten vector u. We've rewritten vector u as the sum of the black vector p and the normal vector here in orange. Okay, folks, I'll now let you guys try this in your in-class work. You get to repeat this procedure that I just did in one of your examples, and then you'll try to find your parallel and normal. Don't worry about drawing a picture here. Instead, just trust your vector algebra as you do this in 3 dimensions. So I'll let you get started on that, and then we'll pick up on the last bit of this section.